This file has an audio description of how to solve the 10th problem in the diffusion and osmosis problem set. The Goldman equation can be used to approximate the resting membrane potential of a cell by taking into account the relative permeabilities of more than one ion. For this problem, assume that the permeability to potassium is 10 times greater than the permeability to sodium. To solve problem 10, substitute into the Goldman equation the values for the ion concentrations and the relative permeabilities of the membrane to potassium and sodium. Remember that for any Nernst equation problem that shows up on a quiz or an exam question, you'll be taking log to the base 10 of either 10 or 0.1. In this problem, it's a little bit more complicated, but you could use a calculator to solve the problem. The answer comes out to be that the membrane potential is negative 58 millivolts. The correct answer for problem 10 is choice B, minus 58 millivolts. For a problem like this, you can always check to see if the value of the membrane potential that you calculate makes sense. For a resting membrane potential where potassium is almost the only contribution to the resting membrane potential, the membrane potential will be very close to the potassium diffusion potential, which is very negative. Minus 58 millivolts is less negative than potassium diffusion potential. It's being offset by a contribution to the resting membrane potential made by permeability to sodium. Sodium is present at much higher levels outside than inside. Sodium diffusion potential is positive, so it makes sense that a contribution to the resting membrane potential from sodium would move the resting membrane potential to a less negative membrane potential than the potassium diffusion potential. So minus 58 millivolts is a little bit less negative than the potassium diffusion potential. So you can tell that minus 58 millivolts is in the correct ballpark for the solution to this problem.